Think everyone, any questions for classic actions? Any question you have? This is an example of working in the test. If you write out the set, make sure you expand what you use. Because if you don't expand, if you don't understand your working, then you will not understand. You don't need to write down the full sentence, just say what you use by definition or by laws and so on. Any question? Okay, if not, we'll start the lecture today. Today we'll talk about functions and metrics. We'll not go into too deep into functions or metrics, but there's some language that we need to all master and learn so that we can talk about these objects. Maybe yesterday I got a bit too fast, so because I thought you guys might learn more. So maybe today I will speak a bit clearer. and a bit slower. Okay, let's try. So today we'll talk about functions. So before we already talk about propositional logic, set theory, okay, we use propositional logic to describe element and set theory to group the objects that have similar pattern. Now we want to study map between objects. Is the sound okay or not? Okay. So now we want to study functions. So we want to have map between sets. Okay. So let's start with two non-empty sets. Okay, so what's the function is? So function is I give you an input, give me an output. So it is an assignment of one object, exactly one only, one and only one, of B to every element of A. Okay. So we will write FA equals to B. Okay. So if B is the unique element of unique element of B assigned to A by F. Yeah. So we write that the map from A to B. Okay. So sometimes we'll call this mapping of transformation. For example, the map, the real map, the map of the Earth is the mapping of the Earth to the paper. Okay, so it's also a function. So Earth is a set, and then paper is a set. The point on the paper is a set, and then the whole Earth, the point in the Earth is a set. Okay, it's all mapping. Okay, so 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 given a function, okay, we said that A is the domain of F. Okay. And then B is the co-domain of F. Okay. And then if FA equals to B, we say that B is the image of A, and A is the image of B. Okay? And then all the place that F can reach in the codomain is called range. So the range, or sometimes we just say image, is the set of all images of in A. Okay. So range is FA in the set builder notation. We write Y, sorry, just say B in B and B in B, such that B equals to FA for sum A. Okay. So this is the range. Note that the range is always a subset. It's always a subset of codomain. Okay. So the cardinality is less than is less than equal to codomain. Okay. So domain, every domain or every element in the domain, we know where it gets sent to, but we might not reach all the elements in the codomain. Those we can reach are called the range of the image. Okay. Okay, let's give an example of functions. Okay, so give an example of functions. So, for example, we look at the function from real to real, sending x to x squared. And so this is a function. You give me x, I hand you back a x squared. And second, we also look at the function from R to R by sending x to x cubed. So this is also a function. So let's call G. Okay. So depend on what the codomain is, name your function differently. So a function is called real value. The value is real if the codomain consists of real numbers. Okay, and it is called integer value, which is discrete if codomain is Z. Okay, so similarly, this function also has algebra structure. Okay, so algebra structure, you need two operation. Remember last time we encountered two algebras, the logic, propositional logic, and all, and also the set theory, intersection and union. So function also have algebra structure. Okay. So we can add function together. We can also multiply function together. Okay. So these are mapped from A to R. Okay. So it should define for every element in your domain. Okay. So how would you define the sum? So we define them as a pointwise addition. So this means I can compute f1x because f1 is a function, yeah, because f2 is a function, yeah, and then after I put this input in, I get a real number. So I can add the real number together. So that means I put in the input, okay, and then it split out a sum of real numbers. Okay, it's still a map from your your domain to R. Okay. How about F1, the product of F1, F2? You also can define it as a pointwise multiplication. Okay. So I know the value of f1x, I know the value of f2x because they are the function. So I can multiply together to get a real number. Okay. So one good exercise to do is to check that this actually is defined uh, defined as function function from the definition. Okay. So you need to check that every element of that you get sent to a unique element in real in your codomain. Okay. So for example, just now we have this fx equal to should I write fx equal to x squared and gx equal to s cubed. So what is g plus f acting on x, which is gx plus fx, which is x squared s cubed plus x squared. Yeah, s squared plus s cubed is equal to s cubed plus x squared is because the commutativity of the addition. How about gfx? Gfx is gx times fx, which is s cubed times s squared, which is x to the power of 5. Okay. 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 So a remark here, right? So instead of looking at the whole set, domain set, we can also look at the subset of domain and then define a similar range for that subset. Okay, so we can take smallest set here. Okay, that's fine. Okay, next. So there are few properties, I mean, maybe two properties of the function that we are interested in. Whether the function, first of all, is whether the function is one-to-one or not. Okay. So being a function, you cannot be one to many. So because for every input, it only gets sent to one place. It cannot get sent to two pairs. If it gets sent to two pairs, I don't know which one to take. So it cannot be one to many to be a function. And the question is whether it's many to one or one to one. So a function is one to one or in injection. If and only if, okay, the condition is if the image is the same, okay, then the pre-image should be the same as well. Okay, so if then relation. If then. So sometimes we say that f is injective. And then we will use the notation, the hook notation. Okay. Like A is sitting inside B. Okay. Because it's one to one, right? One to one. So every element in A have a unique one in B. So your A is like sitting inside B. So you got an injection B. if you want to imagine, right? So every one of them get mapped into a B dot. Yeah, that's why we use a hook, like a subset. Okay. So for example, fx equal to x squared is not injective. Why? Fx equal to x squared is not injective. Huh? For example? Okay, good. So if you look at -2, you get 4. If you look at 2, you get 3. So it's like two two different distinct elements get sent to the same element. So it's not injective. But gx equal to s cubed is injective. Okay. So how to show gx equal to s cubed is injective? Huh? Why? So and then okay. But this one to show injective, you need to show for all. Yeah, for all. Not injective, you just need to pick one, right? Because negate the Morgan's law, negate for all you get existential, and then but injective you need to show for all, right? So you assume so you assume gx equal to gy first, right? So you want to show x equal to 1. Right, this is the definition. So, so gx equal to gy, by assumption, we get s cubed equal to y cubed. So how to get s equal to 1? S, s cubed minus y cubed equal to 0, and then open, factorize. How to factorize? You sure? You say like this. You want to factorize what? X minus y. Huh? Right. Look, like this. X y. Right. Is that oh, huh? Pass. Oh, can. Oh, but oh, wait. So either this one equal to 0 or this one equal to 0. But if this one not equal to 0, how you I'll say So you need to make sure this one is not 0. So that this is always 0. So this one is positive. This one is positive. So is this one always positive? So Use what? What's that? Huh? Delta? What's delta? Huh? How to use delta? Oh, discriminant. Okay. So find the root. Okay. So find the root. B square. Okay. B equals minus 4AC. Okay. So B square. But X and Y, I don't know what are they, right? B square minus 4. Discriminant. Okay. So discriminant for A, C. So what's this? So this one depend on X and Y. Okay, so this one depend on X and Y. So let's huh? B squared minus 4x. Huh? B square is 1. No. B square is not 1. Wait. Oh, wait. Okay, sorry. Y, yeah, right. Sorry. B square minus 4ac. Okay, right. So this one is 1. So one is so minus 3y squared. So this discriminant depend on y. It doesn't depend on y. So this one is minus. Also, this one is complex root, right? So this one is less than 0. Because y squared is 0, minus 3 is negative. So discriminant is less than 0. So this is a complex root. So x is a complex root. Instead of 0, this is a complex root. So how? So does this imply that this part have to be 0? This discriminant is 0. So y is a complex. So if x squared plus xy plus y squared is 0, then um then x is complex. Since the determinant is less than 0, so uh, does this imply this cannot be 0? Uh, oh, huh?
We make assumption that
Uh-huh.
X must be real, then we will lead to a contradiction.
Make an assumption that x is real. X is actually real, but how do we work? So you say that if we assume that x is real, then you cannot obtain the root. Okay, I think okay. I think can. Okay, I think can. So so g is a function from real to real, right? So we want this equality to hold in real. So so this part here doesn't have a root in real. So this part cannot be equal to 0. So this part must be equal to 0. So it's equal to 1. Okay. Huh? What? Oh, one more time. Okay. So since our function is going from real to real, okay, the number here we consider are in real. Okay. So this polynomial here have no roots in real because any number you plug in, you won't get zero unless you have a complex number here. Okay. Because we find the discriminant is less than zero. Okay. And then so for this equation to be true, and this factor here has to be zero. So if this factor here is zero, then x minus y equal to zero, then x equal to one. Okay. Okay, very good. So, okay, because yesterday I didn't give them this answer, I just show where it's a theory, which strictly increasing function is 1 to 1. And we will see that gx equal to s cubed is a strictly increasing function. Okay. Very good, very good. Okay, next. So yeah. So now I want to talk about strictly increasing functions. Okay. So let f be a function from a to b, and a is in real, and then b is also in real. Okay. So this function is called increasing if fx less than equal to f1 for every x less than 1. Oh, I'm a bit lazy here. I okay, maybe I just say whenever x less than 1. Okay, and then we said that it is strictly increasing if fx is strictly less than 1, f1, whenever x less than 1. Okay. And then decreasing if fx greater or equal to f1 whenever x less than 1. And then strictly increasing, strictly decreasing if fx greater than f1 whenever x less than 1. Okay, and then x and y are in the, for all x and y in the domain of f, so it's a. Okay, so for example, we can show that gx equal to s cubed is strictly increasing. Okay, to show this is convenient to prove by cases. So what's the cases? So I break into positive, non-negative, and negative part. Okay, because these two parts, the algebra is different. So if I look at positive number first, okay, then we will have s cubed, which is x dot x is less than x dot y, which is less than x dot y, which is less than y. Okay, where I just apply the assumption. Okay, so if I want to explain, I just write by assumption. So apply a few times. Okay. Next, do it for the negative number. Yeah. So can you do it? and leave it as an exercise. So to do this, you need to sort a few times. I mean, the identity. You sort a few times to get the identities you want, the inequalities you want. Okay. And next. So next, okay, remember I mentioned that the range not necessarily will reach all the codomain. So if the range is equal to the codomain, then this function will be called onto. Okay. It's onto the codomain. So we call it onto or a surjection. Okay. If and only if for all B in the codomain, you can find some element in the domain such that FA equals to B. Okay. So we also call it F is surjective. So the notation is F A then double head arrow to be surjective. Okay. So for example, fx equal to s squared is not onto. Why is it not onto? So there must be some element in the codomain that it doesn't get mapped to. So why is it not onto? Any ideas?
Because it's always positive.
Yes, because it's always positive. I think this reason we'll hear before, right? In the proposition. So it is always positive. So in particular, so s squared cannot equal to for negative number for all x in where in R. Okay. This is 18. Okay, so how about gx equal to s cubed is onto. Yeah. So if it is onto, then you need to find the pre-image for every element in B. Okay. So for example, in this case, take an arbitrary y in R. Okay. So in the codomain, so this is the codomain. We can pick x equal to cube root y such that g of x, which is g of cube root y, which is cube root y to the cube is 1. Okay. So for every y, for every element in the codomain, okay, you need to find me a image so that you can show something is onto. Okay. So if a function have both of these properties, then we will call it a bijection or one-to-one correspondent. It's a bijection or it is bijective. Or it is one-to-one correspondent. If it is both, It's both 1-to-1 and 0-to. Okay, so maybe we will write F is the hook plus the double adjective. So for example, F equals to S squared is not relative because it's not 1-to-1 and also not 2. GX is adjective. Yeah. Okay. Okay. So in summary, so look at this 5 picture here. So we have the domain ABC and different ABCD or ABC, either ABC or ABCD. And then the codomain we have 1, 2, 3, 4, 1, 2, 3. Okay. So why is this map here, the blue map here, 1-to-1? Because everyone only gets sent to one element in the domain, codomain. And then it's not onto because this guy has no pre-image. Okay. This one, everyone in the codomain has a pre-image. But it's not 1-to-1. Why? Because A and D got sent to the same image. And C is 1-to-1 and not 2. So everyone only gets sent to one different object. And then everyone in the codomain has a pre-image. Okay. And then neither 1-to-1 or 1-to. So not 1-to because 4 have no pre-image. Okay. Not 1-to-1 because 2 has the same different pre-image. And then E. Okay. E is not a function. Why? Because A gets sent to 2 and 4. So you can't decide which one you want to go to. Okay. And then for function, if you want to show it is injective, you need to check for arbitrary x and y. Okay, check for every x and y, and then show that if the image is equal, then the pre-image must be equal. Okay. If it is not injective, you just need to find two elements, x and y, such that their image are equal. So this is like the negation of if E then Q, right? Okay. So if it is surjective, so you need to find for every element in your codomain, you need to find one image. If it is not surjective, you just need to find one element in your codomain such that you can't find the image. Okay, so this is the negation of the proposition. Okay, so why this bijection is interesting? So if to link back to your set theory, to the cardinality of set. So if there's a bijection between two sets, then the cardinality of the two sets is the same. So the cardinality can test the bijection can test the size of your set. Okay. If you have a bijection, then the size is the same. Okay. So still got time. So since we can go from F from A to B, if we have a bijection, so everything is 1-to-1 correspondent. then we can go backward from B to A. And this is called the inverse function. Okay. So suppose we have a bijection from A to B. Now we want to define the inverse function. So it's a 1-to-1 onto. Okay. So the inverse function of F is a function. So since it is a function, okay, from where to where? From okay, let me write down the notation for it first. It's a function F inverse from B to A. So that means you give me a B, I need to give you a A. So how do I give you this A? So it should be defined by assign to an element B in B, the unique A in A, such that F A equals to B. So you give me a B, I go and find this A using the bijection I have, right? Because since it's the bijection, it is onto. So if it is onto, then I can find the pre-image. So this is the AIT. So hence F inverse of B is A. Okay. Then we also call F is invertible. So F is bijection, F is bijective, and then we can find the inverse function, then F is invertible. Okay, for example, Fx equal to x squared is not invertible. Why? Because Fx, F minus 2 is equal to F2 equal to 4. Okay. So if you give me a 4, I don't know whether I want to go to minus 2 or 2. So there's some ambiguity on defining the F inverse. Okay. But if we look at S cube, Gx equal to S cube is invertible. Okay. Why? Because we can just take, like what we did just now, we just take, just take, let's consider us. Why? You give me a y, give me a cube, y. So this is the pre-image, right? Just now we work out the pre-image of y, remember? So let's go back. Yeah. So we got the image and then we found the pre-image. So you guys want to recall how to find the inverse function? I think you guys learned how to find inverse function before. Suppose gx equal to y. Hey, wait. So you guys learned how to find inverse function or not before? Yes. Yes. Okay. So what you did is you suppose gx equal to y, and then s cube equals to y, and then solve for x, and then set g inverse x equals to x. Right. So now, after you learn this definition, right? So actually, what you did is you look at every element in your codomain, okay, and then you find the pre-image. Okay. and you set your function as your pre-image. Okay. Yeah. So I'm not sure about you, but when I did the high school math, I don't know what these are doing. I just follow the step. But only after this definition here, only I know what this step. Any question? Yep. Which? Yeah. This one. This one. This one. Nothing here. Uh-huh. Why I write like that? What do you mean? You mean how to set G inverse? Oh, okay. Wait, first of all, is this what you did in your secondary school or high school? No? I'm not very sure, I forgot already. Okay, never mind. Okay. But okay. So what I did here is I found the pre-image for y. Okay, so this is the pre-image of y. So the definition of inverse function is send your b to the pre-image. Send your b to the pre-image. Okay. So I start with the codomain, and then I found the pre-image, and then I set the thing to equal to the pre-image. Yeah. 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 X here doesn't matter, even put Z also can, even put W also can. But the main thing is to send it back to the pre-image and then find the pre-image. That's the key. Any other question? Find the pre-image. Any other question? Ah. Yeah. Uh-huh. You mean if it is 1-to-1, there's an inverse function? No, because you know why? Okay, are you saying if 1-to-1 to if it is 1-to-1, is it enough to define an inverse function? Is it? Okay. It is not because to. Okay, so the question is, I think this is a good question. So if f is 1-to-1, is it can I define f inverse? Okay, so to define f inverse, right, you need to, for every b in B, you need to tell me how to send to f. So if it is just 1-to-1 and not onto, then I don't know where this person have to go. Okay, but if it is 1-to-1, if you restrict to the range of f, then you can define the inverse. Because the range of f is where the f can achieve. But if you restrict, can I define that? Only if you restrict f in, how to say, you restrict yourself to f a. Okay, so if you look at a smaller, so for example, for this table here, so if you throw these two out, then you can define the first function. Okay, Otherwise, this one have no arrow. I don't know where to go. Okay. Any other question or not? No? No question. We break for 10 minutes. 10:05, 03, then we come.
你刚才讲的这个那个只有 one to one 的时候，只有那个 on two 的时候，你可以就是可以证明这个那个 inverse，那有没有什么反例呢？
是
就刚才他提的那个问题，有没有什么反例？刚才那个
这个就是反例啊，这个不是反例。
这个我没想到函数，
什么意思？
没想到有个实际函数。
哦，有想一下啊，有。如果你
X 的范围小在
有你要实际函数，这个啊，然后你可以把这个把所有的数据送去那个算数，那你单数就没有人遇到它，就没有人会
对，
懂什么意思？
我知道
啊。
那双数对应回来对应回来，
像单数就没人就遇不到单数。
但是它每一个 inverse 都有一个原函数 x 和它对应的，这也不影响它那个。
没有啊，不能啊，这样你不能够。如果你要再 define 一个 f inverse 啊，那你就不知道那些单数要去哪里。
单数不管，
啊，
单数不管，
不管，
对啊，
为什么不管？
因为你 inverse 就是求它那个，就是能不能推导出来原函数。
不是，
它这个逆
不是，对，所以你看那个定义，你看那个定义，
不是看这儿，
然后你看，
对啊，在哪里？然后我们这也有。这我方向有很多事情，我
然后
这好像不是那种我找有没有那种确认有没有？
你要说什么？你就想说什么？
就那个 O2 对吧？
啊，对，怎么样？
刚才说的是就把单数抛去了，但是你双数的 inverse 回来还是能找到对应的单数。
但是问题是哦，你看你这个function啊，它 define 是从它的 core domain去 A 哦，你不能说我只 define for 一部分的，你明白吗？
我知道，
啊，
想想啊，
所以你也要告诉我单数去哪里，除了告诉我单数，但是你告诉我不出就不能。因为 function 的定义就是要每一个这个里面都没的东西，你都要给我一个那个，看每一个A 里面的东西，你都要给我。所以反的话，就每一个 B 里面的东西都要给我，每一个都要。所以它是一个package，一个配套。function 的配套就是每一个 A 都要给我。两个行。Yeah. Oh, this one right? Yeah, hold on. Not already changed, though. Not yet changed. I thought I changed already. Which? This one? I know. This one is lecture 8. Last week. I thought I changed already. I think I'm pretty sure I changed already, but let me see. Lecture 8. Oh, 7. Yeah, 7 is wrong. Yeah. Look at the 8 one. Yeah, look at the 8 one. Maybe I need to delete those. Yeah, look at the 8.
我接触了100个，是啊，没有爬树啊。OK。
我吗？我一般会全吃。
So done, ready? Ready, done. Done? Hello? Ready? Ready? Ready to start? Okay. Hello? Hello, ready? Hello? Yes, okay, good. Okay, so next we know how to multiply function, we know how to add function. Now we can consider another operation which is the composite. Okay. So suppose G is a map from B to C and F is a map from A to B. Okay. Then we can compose these two functions if they have a similar domain or codomain. Okay, let's see. So the composition of F and G is denoted by FG and such that, wait, let me see. There is a function from where to where? From A all the way to C, defined by, for every element in A, and we have F, G, and equals to, we do GA first, and then GA land in B, and then you can do, wait, okay, wrong way, sorry. So let's define GF. Okay. So we will do F on A first, okay? So F send A to something in B, and then we can do G. Okay, this one is correct. So here is a function on an element. Here is I apply F to A first, and then this become an element in B, okay, and then I apply G, and then let's get an element in C. So this is a function applied on the element. I get an element. Okay, make sure you know how to read this. So these two is by definition. Okay, so here is a function. Here is the applying function. Okay, so one way to check whether you found the right inverse or not, right? So one way to find is through this theorem here. So if you f is an invertible function, okay. So then you can check that actually f inverse is the identity function, and f inverse f is the identity function, where ID is the identity function. What's the identity function? Identity function sends every element, sending every element to itself. Okay, this is the identity function. So, itself. Or in other words, I send x to x. Okay. So for example, just now we get gx equal to s cubed. Okay, and then we propose G inverse X to be cube root X. Okay, so two things to check. Check G inverse, and also check G inverse G. So we want to show that G inverse is identity function, and then G inverse G is identity. Okay. So to show that it's an identity function, you just need to check on the elements. So you check whether they got sent to themselves. So G inverse X is G inverse X, which is G cube root X, which is cube root X, which is X. How about G inverse GX? So you get G inverse on GX, and then you get G inverse S cube, and then cube root X. Yeah. So like sort the order of putting the cube and square. Okay, this is a theorem, but we just use it. Okay, I disappear. Okay. See. Okay. Next. So next we define a graph. A sketch graph in the high school before. We will define what is the graph here. So let f be a function from A to B. Okay. So the graph of f is the ordered pair. Okay, last week we learned the n tuples, right? So now it's just the ordered pairs. Okay. So ordered pairs of A, B, okay, such that A is in A times B is in B. So this is the Cartesian product. Remember the Cartesian product of A and B? Okay, it's just the order pairs. Such that A is in A, and what B we take is only those that has the pre-image. Okay. Yeah, so maybe we could just write A and FA. Simplify the notation. Okay. So for example, yeah, if we look at the discrete version of S squared, for example, we take discrete version of S squared, the function x squared. So we look at the z cross z letters. So z is like -1, -2, -1, and then 0, 1, 2, and so on. Okay. So we have a lattice crossing z cross z letters. Okay. Okay, let's stop here first. Then okay, so let's start with 0, 0 here. Okay, let's call this 0, 0. And then this one is a 1, 0. This one is yeah, this is the 0, 1. Okay, and then so on. So 0, 0 is the point in our graph. So we label it. Okay. And then the next point is 1, 1. Okay, 1, 1. 1, 1. Then minus 1, 1 also is a point because you square minus 1, you get 1. And then 2, 4. Okay, 2, 4. And then minus 2, 4. Okay. And then 3, 9. 1, 2, 1, 2, 3, 4, 5, 6. Okay, somewhere around here. Somewhere around here. Okay. So this is the graph of this discrete S square. But if you turn this into R, so if instead we look at R, so if you look at the R, okay, so R is discrete, so you could link all these points together. Discrete. Okay. Then this S square is the S square C. Okay, so this is the graph of rectangular S square. Okay. Okay, next we define some special function. I think is useful for you guys. So first we define the floor function. So a floor function is a function from R to Z. Okay. So how is it defined? So it assigns every real number, okay, to the largest integer that is less than equal to x. Okay. The other one is ceiling. The ceiling function also from R to Z. Okay, give you an integer. Assign every real number to the smallest integer that is greater or equal to x. Okay. So for example, floor, take floor on the 6.5. What do you get? 6. If you take floor on 7.25, what do you get? 7. Okay. You take ceiling on 6.6, what do you get? 6.6. What do you get? 7. If you get ceiling on 7.25, what do you get? 8. Yeah, good. So this floor function satisfy a few nice properties. In particular, this 3AB, so it's like can move the scalar up nicely. You can move the -1 up, and then just look at the real number, the modulus real number. And also you can move the addition of scalar up again, so that you this n is what? N is an integer. Okay. So you can move any integer out. That means to look at 6.5, you can just move the 6 out and then look at the 0.5. So you just need to consider the decimal place. Okay. Okay. So next, let's go into matrix. matrices. Have you guys learned matrices before? No. Oh, same situation as the last one. Okay, so this is the first. Hey, you guys need to take linear algebra on the course. Oh, when already check. Hey, so is it linear algebra include matrices? Oh, yes, okay. Check. Forget already. Okay. Never mind. Not deep also this matrix. So okay, so matrix is a rectangular arrays of numbers. So matrix have m rows and n columns. So let me write it out first and then draw it out. Okay, for example, you have like something like 2, 5, 6, 7. Okay, so here we got 3 rows and 3 columns. So it's like 3 times 3. Okay. So not to confuse you, so I put this. Okay. If m equal to n, then it's called a square matrix. Which the example above is the square matrix. Okay, so square matrix have same numbers of rows and columns. I think one good this notation for matrix you need to learn. This is how you describe matrix to computer. So let A be a m by n matrix. So you label each entry of your matrix as Aij. So you got A11, A12, A13, and then A1n. So the first one is for your row, and then the second one is for your column. So the next one is A21, A22, A23, and then another A2n. Yeah. And then and so on, you will reach AM1, and then and so on. AM2, AM3, then AM. Okay, so what? So you need to so you need to observe this diagonal term here is you see this ij is the same. Okay, this is one of the feature of the diagonal. If we just study a square, then here we'll reach AMM or ANN. But this one may be rectangular. Okay. So if we talk about the I row of A, so it's a row, so it's a row matrix, 1 by n matrix. And 1 by n matrix is AI1, AI2 up to AI. And then the J column is what? The column matrix, which is the m by 1 matrix. It's a standing matrix. A1J, A2J up to AJ. Okay. So compact so the IJ element entry of A is AIJ. Okay. So compactly, we can just write A equals to bracket AIJ. Okay. So if you want to specify the range of I and J, you can write it here. Okay. So maybe I is M and then J is. Okay. So to tell people how big is your A. Okay. Next. So you got two matrices. What can you do with them? Huh? Multiplication. Okay. But the easiest one will be first add them first. Okay. So let us add them together. Okay. So we define the sum. Okay. AB. Okay. Right. So when you want to add them, right, they have to be with the same size. So we start with the same size. Okay. If they're different size, we don't know how to add them because we can add them differently. Right. So there's ambiguity. So we'll make sure they have the same size first and then add them. How to add them? Add them column by column. Okay. It's the M by N matrix that has AIJ. So if you want to write out the notation, you will get AIJ. Okay. So for example, if you want to add these two matrices together, what do you get? 7, 8, 9, 2. Okay. So next, as your friend suggests, we can multiply them together. So when we multiply them together, there's some condition on your size. Okay. So one size is M times K. The other size should be K times something. Okay. So that the product A and B, we write AB is a M times N matrix. Okay. Such that, okay, let me write A dot B equals to what? Equals to AI1 B1 J times A. Okay, so what's this notation here? So I take the row matrix, the row matrix times the column matrix of the second. So for example, this picture here. So if I want to multiply two matrices together, so I take the first row, okay, multiply the first column, and then I get first entry here. So so this one here, and then the one here at the end. So all these form the first entry, the 1 1 entry. And then if you take the first row and then times the second column, you will get a 1 2 entry. Okay, first row and column, you get a 1 n entry. Okay, for example, let me do it so that you can remember. Okay, let's do 2 3 1 2 with 2 3 1 2 1 1. Okay. This one cannot multiply together, right? This one 2 times 2. This one 3 times 2. Okay. So change this. So this one wrong. So maybe change again. Maybe change the longer to the horizontal one. So like this. Okay. So this one is what? This one is 2 times 2 times 2 times 3. So in the end, you will get 2 times 3 matrix. Okay. So what do you get for the first one? So you get 2 times 2 plus 3 times 1. Okay. Okay. And then the second one, you get 2 times 3 times plus 3 times 2. And then the fourth one, the third one, you get 2 times 1 plus 3 times 1. Okay, the last row I don't want to write, I just compute. So 1 times 2 plus this one is 4. This one is what? 3 plus 4, 7. 1 plus 2, 3. Okay. So I should write this one is the size 2. Okay. As an example so that you know what I'm doing in the figure. So you can see that this matrix, right, share similar property as function. Okay. So some of the function can be expressed as a matrix. And then use matrix theory to study them. Okay. So turn is like turning the question from not calculus but function into linear algebra. Sometimes linear algebra is easier to study. Do you learn eigenvalues in your eigenvectors? Eigenvalue, eigenvectors, yeah. So eigenvalue, eigenvectors are some property that function could have. And then if we can turn the function into matrix, then we can use matrix to study them. Yeah, this is what the representation theory study, which is my research area. And then next. So next we have this, just now we introduced the identity function, right? So now we also introduce this identity matrix. Identity matrix. Okay. So you say, identity function send elements to elements. So is identity matrix sending some vector, some element to itself? Yeah, so the answer is yes, but let me write down the definition of this identity matrix first. So identity matrix can be described as described by this Kronecker delta. So it is 1 if I equals to j. If it is I not equal to j, then it is 0 and 3. So it looks like this. So since this is a square matrix, right? So when I equals j is the diagonal. And then the other part is 0. Okay. So in the I2 case, okay, you get 1, 1, 0, 0. Okay. So this guy, so this matrix, right? So m by n matrix, okay, is a map from Rn to Rm. Okay. What's Rn? Rm. So Rn is the Cartesian product n times. So m is m times. So the things inside here is a vector. So for example, I2 is a map from R2 to R2. Okay, it's a function from R2 to R2. So how it acts, I think you know how to multiply matrix with vector. You know? Yeah. Okay, so this is a what? This is a 2 by 2, and then this is a 2 by 1, right? Just now we learned already how to multiply. So this one we will get A and B. So you get back to its identity matrix. Okay. And what else? Okay. So wait. Let me come back. So similarly, a matrix can be invertible. Okay. So when is it invertible? If we can find a inverse matrix. If there is an inverse matrix, such that it is the left inverse A and also it is the right inverse to A. Yeah. So if you have another matrix, you multiply together, you get identity, then this is invertible. Okay, good. Next one, we can introduce another operation on matrix where you can transpose your matrix. Okay, you turn the row into the column. N by N matrix. So the transpose of A, we write as A transpose is the N by N matrix. So we swap the row and column obtained by interchanging the rows and columns. Rows and columns. Okay. So AT is what? AT is just AJI. Okay. So I think if I give you an example, you should. So for example, 1, 2, 3, 3, 2, 1. You transpose it, you get 1, 2, 3, 3, 2. Yeah. So you make the row become a column, make the row. Okay. So this transpose have some nice property when the matrix is square. Okay. So we call that a square matrix is symmetric over the diagonal if A equals to AT. Okay. So for example, what matrix is symmetric? So we encounter this identity matrix. So identity matrix is symmetric. Okay, if you swap it, you still get the same matrix. And then also this matrix is symmetric. But we won't go further from here. But next. Okay. Okay, next. What do we have? Okay. Okay. So next, we try to transform the Boolean algebra. Remember we learned the true, true, false, 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 something. Okay, that that algebra. So we try to compute them. Try to compute a lot of these operation together at one go. So we organize them into a matrix. Okay. So let's study this matrix here. So different area have different kind of matrix to study. If you are statistic, then you will study the matrix that has every entry, that every row and column sum to 1. Okay, so but in maybe in discrete math, we will study this matrix that have entry that are either 0 or 1. Okay, example 0, 1 matrix. Okay. So recall the Boolean algebra, the Boolean arithmetic. So it's the N and O, or the intersection and the union. Okay. So if B1 and B2, you get 1 if both of them are 1. Okay. If 0, otherwise. So B1 or B2 is 1 if B1 is 1 or B2 is 1 and 0. Okay. So given two 0 to 1 matrix, okay, so of the same size, we can define two things. One is the join, one is the mid. So the join of A, B is another 0 to 1 matrix. Okay. But with entry A and B is have the entry Aij or Bij. Okay. See, now you really see this like this all as an N, as a plus now. Okay. And then the mid, okay, the mid B. Actually, I used the wrong. This one is the O, big O. And then is the take N at every entry. Okay. So next, so for example, we have this 1, 1, 0, 1 and 0, 1, 1, 0. What do you get? For the first entry, 0, 1, 0, 0. Okay. How about take the O, take the mid, take the join, sorry. 1, 1, 1, 1, 1. Okay. 1, 1, 1. Okay, good. So you have plus, you have multiply, you can not yet. Just these two. And then we can define the Boolean product. So if you want to define Boolean product, you also need to have the size measure. So one is m times k 0, 1 matrix. And then the other is k times n. Okay. So the Boolean product A times B. Okay. A and B. Okay, we write A circle dot B. Okay. Is the entry what? Defined as AI1 with A1J. Okay, this is the same, no, I mean similar operation as the multiplication, just like change the plus and all into this join and big in. Right. So is the first row and then this one is join or mid, join mid with the first column, and you add them. Okay, for example, let's do this. So let's take the product of these two. Okay. So the first entry you get n1 and 1 or 1 and 0. Okay. And then the second entry you get n1 and 0 or 1 and 1. And then 0 and 1 or 1 and 0. And then 0 and 0 or 1 and 1. So what do you get? What do you get? 0. 1, 1, 0. 1, 0. Okay? Yeah. Yeah. Any question? No? Any question about? No question. Yeah, so this course is like study a lot of subject, but not deep. It's like just one is just learn the language, the other maybe it's just learn the basic. So it's like touch a bit and then go to the next one. Touch a bit and then go to the next. Huh?
Very discrete.
Very what?
Discrete.
Very discrete. Yeah, very discrete. It's really discrete. Discrete method. Yeah, so this all this chapter itself, every chapter can be expanded into the whole semester course. If no question, then we can take a break. 10:56. Okay, thank you.
我们有3
啊？
我们只有 quiz 和 midterm 还有
对
3
对，没有三个，没有三个，
前奏。
只有啊，没有三个。
，quiz 一共有几次
？5次。这个3分很危险嘞，考试不会考啊。
你们出一点点那种题目给我们做一下，就当做考前的预热这样。
考前预热哈
每。次考前的时候，本来都试卷，
不知道。
让我们练练小训的。
等我出完题先。
是，那是对。
等我出完题先。
我也是。哎，我刚连课都挺高的，真的。
我前两天完全发画了。
我这 OK。
没有啊，因为那太早，我们才3天，才3天啊，所以
3个礼拜是6天。
你是会试上课，还是会打？
我是微课，我是
对啊，现在还不够多啊，所以直接放肆就。
这是一共我一次没参加175的。我们要
没有，
口罩。不是，那学校刚才给我发邮件搞口罩是吧？
那个最后的时候去发对吧？
啊，
Yep.
What is the agenda?
Meet is you. Okay. The end.
Alright.
Yeah.
他邮件然后忙关系吗？
Yeah, hello. You can start doing tutorial questions. Feel free to discuss with your friends, and then we will do group discussion 11:30. Definition. Yeah.呀，你写的，这个我知道。对呀，你就成本，呀，就成本。
我记得还有一个可以推本，好像是来进行一些运算，但是我忘了。
没有吧？没有，应该没有吧？应该没有。哦，有，叫做 core factor。
是这个吗？是这个
找那个 minor，
这个
这个什么？
这个是它那个叫什么半
你看这个
我记得有一个是什么，想不起来了，是 a 的 b 等于这个玩意儿，是这个
啊，应该是，对，core factor。但是这也是在做这个，
这个也是在找，这个也在找。
嗯，
找这个，找这个，
找这个，爱奇艺找这个。我看是
对对对对，这样子也不要那个买的，就每一个，不是每个，每一个，
哎也得算。
对。
逆是只有一个逆的逆性，就是任何对吧？ 我们原来应该是同时的，就那个球的逆。 A 乘 B 是什么意思？没有，就是集合在一起，但是你选。光可能就是说，咱学过，咱学在里边。哎，哦，这里。它
Hello, testing. Okay, let's try what you have. Okay, so you will notice that I put some proof question, I put some computational question inside your tutorial. So your test will be something similar to this question. Okay. So these are all the skills you need to learn. You need to know how to compute, you need to know how to apply the theory. Okay, so 2.2.32, okay. Suppose A union B and equal to C union B. Okay, is it A equal to C? So no. Come up with this natural number and the irrational number. They are not equal. And then how about if I change the union to intersection? Also not equal. I can come up with this N with Z again. I mean Z and the Q again, but intersect with N. And then if the union is the same and the intersection is the same, then you can show that A equals to B. Okay. So to show A equals to B, you show the two subset, two set equation. Okay. Then yeah. Okay, I just keep going, and then if you have any question, you just stop me, or just feel free to ask me to come back. And then 2.2.52, yeah, you want to prove cardinality of 3 unions. Okay, so in the class I only tell you about 2 unions, but you can use 2 unions to prove the 3 unions. This is like the example. Okay, so similarly you can extend this to a 4 union, and then keep going 5 union, 6 union, and then keep. Okay, 2.3.2. So decide whether these are function or not. So first one, Fn equal to plus minus n. It's not a function because one number gets sent to 2. Don't know which one to send. Okay. The second one, n to square root n squared plus 1. Right. So this is a function. Fn equal to 1 over n squared minus 4. This is not a function because if you put in 2 and minus 2, then it's 1 over 0. So it's not defined. Unless you throw away 2 and minus 2 in your domain, then this function is defined. And then 2.3.8 is about the floor ceiling function. So do it and then maybe you can check your answer. And then 2.3.10 and 11. Okay, I just put these two together because just check one go whether they are one-to-one or one-to-one. So these two, this is a map from ABCD to ABCD itself. Okay, so first one is one-to-one and on-to because everyone gets sent to different element and then every element in the codomain have a pre-match. And then B, not one-to-one, not on-to, because AB gets sent to B, and then nothing sent to A. C, not one-to-one, also not on-to. Okay. So for this finite set, you notice that if it is not one-to-one, it's automatically not on. Okay. Yeah, just for finite case, finite set. 2.3.22 show that it is a bijection, so you show that it's one-to-one. Suppose fx equal to fy, and then show that x equal to 1 by definition. Okay. So by definition, it is one-to-one. So to show that it's surjective, so every element in your codomain, you have to find me a pre-match, okay, such that when you apply F, you get 1. Find pre-image for surjective. Okay. B, not bijective because not one-to-one and on-to. Okay. Not one-to-one is easy to show, I think. So within the class, 2 minus 2. Okay. Not onto, you also find the point that it's not mapped. Okay. I think somewhere above 7 words. Okay. Next, C. C is not onto, okay, because if you let the function equal to 1, then you cannot find the pre-match. Okay. You will reach a contradiction. If you want to plot the graph, okay, so you can simplify this function here, okay, and then you will get this simple graph 1 over x, and then try to shift it on the x value, and then shift it, reflect it, and then shift it on the y value. Okay. Fx equal to x to the power 5 plus 1. This one a bit trickier maybe. So yeah, show that it's one-to-one and onto. Okay, onto should be easy. It's similar to the S cube. Okay, you find the pre-match. But one-to-one, maybe harder to factorize now. So instead, you can show that f is strictly increasing. Okay, show that f is strictly increasing, like S cube. Then from strictly increasing, you can show that it is one-to-one. Okay. So one thing, one statement to note here is if f is strictly, so need to show this if f is strictly increasing, then f is one-to-one. Okay. Okay, next, if you have the composite to be onto, then f must be onto. Okay, the outside one must be onto. So this question, this 2.3.34 is to test whether you understand the definition of onto or not. And one onto, and also one-to-one and bijection. So for this case, if you want to show that f is onto, then you have to take an element in C and then show that there's an element in B such that FB equal to C. So you take one element in C, okay, but we know that the composite is on 2. Okay, so we can go all the way back to A. Okay, we can find an element in A such that FGX equal to 1. Okay, but GX, note that GX is an element in B. So you just take the GX to be the preimage of Y under F. So you found a preimage in B. Okay. Next, if the composite is 1-to-1, then G must be also 1-to-1. Okay. So you want to show that G is 1-to-1, by definition, start with Gx equal to Gy. Then you want to show that X equal to Y. Okay. So in this case, you can use the 1-to-1 of F composed G. Okay. And then this one, if F composed G is a bijection, which means it is 1-to-1 and 2, then show that G is on 2, the inside one is on 2, if and only if the outside one is 1-to-1. Okay. Show 2 direction. This direction and then the backward direction. Okay. 2.6.2 is just calculate to make sure you know how to calculate, do simple calculation. Add the matrix, and then 2.6.2 is multiply the matrix. Okay? Yeah, 6.2, 2.6.4. 2.6.19, I think although this one is the odd question, but I added in because I think you have to know this is a 2x2 matrix, the inverse of 2x2 matrix. So it's you swap the diagonal term, and then you add a minus to the other diagonal, and then divide by AD minus BC. And then to show that it's inverse, you just need to check, by definition, just need to check the equality. This means it is a left inverse, and then this means it is a right inverse, and then they coincide. Left and right. And then I include this 2.6.21 because I want to show you the power of inductive proof by induction. So even in matrix, you also can prove by induction. But I think in the middle, you need an extra step here, or you need to prove a lemma first. So if A, B, and A are invertible, then the inverse of AB is B inverse A inverse. So you sort the place and then you put inverse. Okay. But to check this is just like how you check the inverse of the 2x2 matrix. You just multiply on the left, multiply on the right, and then show that it's identity. So, okay. 2.6.26. So 2.6.26 is just finally the join, the mid, and then the Boolean product. Okay, I think that's all. Any question you want me to go through in details? Anyone any one that you want me to go into detail? Any question that you see like blank in first three? Don't know how to understand the question. Are you guys lost or you guys are good at it? Huh? Need time to digest. Okay, I also got students and need time to digest together. Yeah. Huh? 34, huh? This one. Okay. Yeah. What do you mean? You mean this one? What is this? Uh-huh. What do you mean? The relation between these two functions.
It's like how do I know that the other is one to one?
Oh, okay. Oh, okay. Okay. So this question says that if let's say if you know the composite is onto, okay. So in real life, right? So maybe you already apply a few functions. So you know the composite is onto, but you want to ask about the individual function is onto or not. How do you how you know whether it's onto or not? But this 3.2.3.34 exercise tells you that if the composite is onto, then the last one must be onto. Okay. Then the last one must be onto. But G don't know whether it's onto or not. G might not be onto, but the last one must be onto. On one-to-one is another different story. So if you know the composite is one-to-one, so you want to ask whether F or G is one-to-one or not. You don't know about F, but G must be one-to-one. So the innermost function must be one-to-one. Okay. So if it is onto, you know about the outermost function. If it is one-to-one, you know about the innermost function. Other function you don't know what whether they are what are they. Okay. Mm. Huh? This one is injective. Injective assume gx equal to gy and then show that x equal to. Injective assume gx equal to gy and then show that the pre-image is the same. X equal to. What do you mean? Part A you show onto, part B you show one-to-one. Two different questions. They are two different questions. And then C is a different variant. If F and G, F compose G is a bijection, and then show that G is onto if only F is on. Okay. These arguments are not hard. Just you need to and then figure out what you want to show, and then find the right candidate for onto, for example. Find the right pre-image. Only 3 steps. Okay. Definition, find the right thing, and then definition. Assumption, definition. Find the right. Any question? None. No. No more? No more? Okay. If you have any more question, you can email me, and then next week we'll have quiz on topic 2 on the second function and matrices. Midterm will cover topic 1, 2, and 3. And then final won't have 1, 2, and 3 anymore. So it's like 4, 5, 6, 7. Final. Yeah. So make sure you master 1, 2, 3 before the mid-sem, because after mid-sem you won't see them anymore.
Yes, sir. Waiting for your notes.
Okay. No question, then we dismiss.
Yes, sir.
Okay, thank you. 哎，
就是把这个是什么原理变到这里？为什么把这个差异是？
都好，1、2、3，大概是8。